All right, I want to continue doing some examples on continuity. The first thing I want to look at is this graph that's made up of a cosine function and a line. And what we want to do is show that this function is continuous on minus infinity to infinity. All right, well, we don't have to do anything except for at one place. Cosine, we know cosine is continuous. And we know that a line is continuous. All we really have to do on this is make sure that these two functions match up. So what we need to do is show that the limit as x goes to 1 of f of x is equal to f of 1. Now we've got the graph here that kind of shows it to us. From the graph we can look at it and see, yeah, it's continuous, because I can trace along here, and I don't have to pick up my pencil when I transition from the cosine part to the line part. But let's do it formally on the side. All right, f of 1 is equal to, let's see, we've got to grab the one with the equal bar, cosine of pi, and cosine of pi is negative 1. Now we'll look at the limit as x goes to 1. Well, we've got to do this from the left and the right. If we're approaching from the left, that means that x is less than 1, so we're up here. Cosine pi x, that should be cosine of pi times 1. Cosine of pi is negative 1. And if we do our other limit, as x goes to 1 from the right side, x is bigger than 1, so that's going to use the second bit. That's the limit as x goes to 1 from the right of x minus 2, so negative 1. So both our left and right-sided limits are the same. So we've got that the overall two-sided limit is equal to negative 1. And we saw up here, f of 1 is also negative 1. So since the limit and the function value are the same, it's continuous. Now that's writing everything out in long form. Really, the only thing we have to check here is that, that it's defined at 1, and that this function and this function give us the same value there. All right, let's look at this next function. Is this function continuous on negative infinity to infinity? All right, now this function looks very much like the one before, but there's a tiny little technical difference that's going to change the answer. If you don't see it, you could pause it and look for it until you find it, but I'm going to go ahead and point it out. The only difference in these two is right here. We've got this function is defined when x is less than 1, and it's defined when x is greater than 1, but it's not defined when x is 1. So this is not continuous. At x equals 1, because f of 1 is undefined. I mean, that's a technicality, but that's enough for us to say this function is not continuous. All right, let's look at this next thing. Find the value of c that makes this function continuous. Okay, really all we need to do is make sure that these two functions, or these two parts of the function, the square root bit and then the line, are equal when x is 1. So let's, I'm going to do this one with Desmos to begin with, but we'll do it by hand as well. So let's see. iPad Desmos, here we go. All right, so I've got the function programmed into Desmos here in red, and I've got a slider that I can move to adjust what C is. So really what I want to do is I want to adjust the C to make this go together. And by doing that, we wind up with C equals 2 as our solution. Now, honestly, it's easier to do this by hand than it is with Desmos. You might say it didn't take that long to slide it around, but I also had to type in the piecewise function, which can be a bit of a pain. So let's do this without Desmos. All we're really doing is we're trying to find the value of C that makes both of those two things equal. So all I really need to do is set them equal to each other and solve for C. All right, so 5 root x equals 3x plus C. All right, how do I do this? Well, I got to get rid of that square root. So let's square both sides. This will give me 25x equals 9x squared plus 6cx plus c squared. Let's move this over so I get 9x squared plus 6c minus 25x plus c squared. Maybe I spoke too soon about this being easier to do, because we've got to solve this equation for C. Oh, wait a second. Wait. This is true. We're solving for C, but we're solving for C when x is 1. Oh yeah, this is simple. Let's scratch this. I'm going to leave this in because let's see. Set equal and solve for C when x equals 1. So this top is just going to give me 5 root 1. And the other one is 3 times 1 plus C. So that's just 5 equals 3 plus C. C is 2. All right. This stuff over here we don't need to do. All right, let's look at this next example. Find the value of b that makes this function continuous. Well, we can do this again with Desmos if we wanted to. I've got that programmed in. Let's see, we've got this function, and we want to adjust b until these two things are equal. So it looks like, just adjusting this together, it looks like it's b should be negative 1.3. But let's zoom in. They're not quite together. So let's see. Can't quite get them to touch. Let's see. Negative 1.33. They're closer. It looks like this is going to be like 1 1/3. Got enough 3's there that now if you zoom in enough, it's not quite there, not quite touching. So let's go back and solve for it manually. All right, so when x equals 2, what we need to do is solve for b when x equals 2. So negative 2/3 of 2 plus 4 equals 2 squared plus b. All right, so that's minus 4/3 plus 4 equals 4 plus b. We can just subtract 4 off of both sides, and b is negative 4/3. And that's it. And if you go back to Desmos, that's what we were approaching. we were approaching b is negative 1 1/3, which is negative 4/3. All right, let's see. Looks like that's it for this section.